Okay, so today we looked at motion in two dimensions. So far we have only been referring to motion in one dimension like north, south, east, west, or forwards, backwards. In this problem you'll see here we talk about a cyclist traveling 5 kilometers east, then 4 kilometers south, then 8 kilometers west. So if it was just east and west, 5 kilometers east, 8 kilometers west, we could say overall that's the same as 3 kilometers west for the displacement. But now we've got this 4 kilometers south in here to think about. So that makes it a two-dimensional problem, no longer a one-dimensional problem. And with two-dimensional problems, you have to deal with them using or geometrically. You can't just deal with them using an equation or algebraically. So the equations of motion we've looked at so far and graphs that we've looked at so far don't apply in this situation because we have a two-dimensional problem. So what we're asked to find is we're asked to find the overall or resultant displacement. So overall or the resultant displacement over here. So we've got to add these displacements together, but we need to do it geometrically. What I'm going to do is I'm going to zoom in on this picture here. And this is a solution from one of your peers in the class. And you can see that there's a diagram over here that sort of shows the displacements joined together. So we've got 5 kilometers east followed by 4 kilometers south followed by 8 kilometers east. Sorry, 5 kilometers west, 8 kilometers east. Sorry, 5 kilometers east, 8 kilometers west. And you can see that when it's drawn this way, there is a right angle triangle that forms here over to the side. So I'm going to zoom out for just a minute and show you a bigger version of this triangle or this shape. So down here you see we have the 4 kilometers, sorry, 5 kilometers to the east here, the 4 kilometers south here, and the 8 kilometers west here, and then the right angle triangle forms. So most students use this approach, which is a good approach to take, where you end up with this right angle triangle here, down here at the bottom. This distance here is 4, the vertical distance here is 4 kilometers, same as over here. And then the reason we've got 3 kilometers down here is because we had 5 kilometers to the east and 8 kilometers to the west. So the nice thing about having this right angle triangle is that we can solve for any unknown quantities using the Pythagorean theorem, and then using the simple trigonometric ratios to find this angle here, which is the direction of the resultant displacement. Now, you might say that this direction is southwest, but it's not exactly southwest. For it to be southwest, there would have to be a 45-degree angle there, and it's not going to be a 45-degree angle because this distance here is 4 and this distance here is only 3. So it's going to be less than 45 degrees. Okay, so going back to the solution up here, what we can do then is, I'm just going to take out this line here. So what we can do is we can analyze this right angle triangle, and we can say using Pythagorean theorem, c squared, or the hypotenuse squared, is equal to the sum of the squares of the other two sides. And so we figure out what that is. We get c squared equals 25, and then square root both sides of the equation to get c on its own, and it comes out to be 5 kilometers. When we write that answer in, it's going to be 5.0 kilometers because we had two significant figures in the numbers that we started off with. Now to find the angle, so we use the tangent ratio. Let's just go back to the triangle here. So we're trying to find this angle up here, and the tangent of this angle, since it's a right angle triangle, the tangent of the angle is equal to opposite over adjacent. So that gives us this 10 question mark equals 3 over 4. So the angle itself will be tan minus 1 of 3 over 4. Tan minus 1 is the opposite of tangent, sometimes called arctangent, and that comes to 37 degrees, which is less than 45 degrees as expected. The answer is shown here down below as 5 kilometers south, 37 degrees west, which is correct. Except again, here we have 5 kilometers, should say 5.0 kilometers to two significant figures. And south 37 degrees west is not usually written like that. It's usually written like this, with a capital S. Capital S for south, 37 degrees west. So this answer here is what we're looking for. I've used the notation delta D is just displacement, and then I put a little r here for resultant displacement. The resultant is what we call the overall displacement. So this is how I'd like you to show it. A couple more things. I've shown here exactly how you get from the tangent equation up here to the angle itself. So we start off with the equation, substitute the numbers, and then again we're doing reverse operations. So if we had c squared equals 25 earlier, we used reverse operations. So we square rooted both sides of that equation to get c equals 5. Now we have tan theta equals 3/4. The reverse operation of tan theta is tan minus 1. So here, if we take tan minus 1 of tan theta, that just leaves us with theta. And on the right hand side we'd have tan minus 1 of 3/4, which comes out to be 37 degrees on your calculator. One quick word about the calculator. Your calculator has to be in degree mode. There are 3 different angle modes called degrees, radians, and gradians. And yours has to be in degree mode to get the angle of 37 degrees. So make sure you can get that on your calculator. So that's how we solve a problem like that, using displacements in more than one direction. One student chose to do it like this. If I zoom in on my diagram here, rather than showing this right angle triangle, what you can do, and it's perfectly acceptable to do it this way, it's just that it turns out to be a lot more work, is if you were to draw a line from here to here, you could then find the length of this green line that I've drawn using Pythagorean theorem here. So if this is 5.0 here, and this is 4.0 here, then we can use the we can use Pythagorean theorem to find the length of this. The problem is that we don't know that that is a right angle up here. In fact, it turns out not to be a right angle. So you can find the length of this resultant vector here. You can find that still, but in order to do it, you would have to use the cosine law. So first of all, you'd have to find this angle so that you could find this angle. Once you've got this angle inside the other triangle, you could use the cosine law to solve for that resulting displacement. So it ends up being a lot more work to do it that way, but you can still do it that way. I'm going to show you tomorrow another method where if you don't have right angle triangles, a way of solving problems like this without having to resort to the cosine law and the sine law, because those tend to be more difficult to solve if you have to use those laws. It's a method called components. It's very often used in physics when you have more than one vector. It's a very powerful method because you can use it for vectors in any direction, and also any number of vectors can be added up fairly easily using the component method. So I will show you that tomorrow. And one final thing then, notice how I've shown these vectors. So I have joined the vectors where the tip of one vector joins onto the tail of the next vector. When you're adding vectors together, you always will add them that way, and it's called adding vectors tip to tail. Tip to tail. So the tip of one vector attaches to the tail of the next vector. You'll notice that doesn't apply here. This resultant vector goes from the beginning of the first vector to the end of the last vector, and I like to show it as being a separate vector. So this delta dr here, that's not one of the displacements we started off from. That represents the sum of them. So I tend to use a different color. I've used red for that vector just to distinguish it from the individual vectors we started off with. And rather than writing the arrow at the tip, I write the arrow in the middle. And there's no particular reason for that other than it does distinguish it from the other vectors more easily. So it's a different color. It's also got the arrow in the middle. So you can easily tell which are the vectors that we started off with. These three here. And then this red one, the resultant one, is equivalent to the sum of those three vectors, or the resultant of them. So that's a common notation as well.